Next, we will learn another classification model, which is called support vector machine. Even if support vector machine is commonly used for classification, we need to know it can also be used for regression. In this lecture, we take classification as an example to introduce support vector machine. So here we introduce support vector machine in the context of classification. So this is also for decision tree. We will introduce how to use decision tree to do classification, but we need to know decision tree can also be used for regression. Now let's look at some background information about support vector machine. Support vector machines were invented or proposed by Wapnick and his co-workers in 1970s. SVM is a linear classifier that finds a hyperplane to separate two classes of data, positive and negative. So here we can see at the beginning, SVM is also used for dealing with a binary classification problem. So the traditional SVM is a linear classifier, but we know in real-world applications, the classes are usually nonlinear, separable. So here we introduced kernel functions to deal with nonlinear separation. SVM not only has a rigorous theoretical foundation, but also performs classification more accurately than most other methods in applications, especially for high-dimensional data. So this is the advantage of support vector machine. Now let's look at what is hyperplane. A hyperplane in an n-dimensional Euclidean space is a n-1 dimensional subset of the space that can divide the space into two disconnected parts. So here, the hyperplane dimension depends on the dimension of the data. For classification task with only two features, so you can think of a hyperplane as a line that linearly classifies a set of data. So if your task has three features, then you can imagine this plane. We can use this plane to separate two classes. Support vector machine is based on the idea of finding a hyperplane that best divides a dataset into classes. It aims to maximize the distance between the hyperplane and the difficult points close to it. For example, let's imagine we have two classes, the red points and the green points. We can see some points, some close points, they are difficult to be separated. If we want to separate the two classes, we can create many hyperplanes like this line, this line, this line, this line. For this point, we can see it's close to this dark red line. We can call it a difficult point. Here, one question is that because we can create many lines to separate these points, so which line should be the best one? So in this example, we can see the yellow line represents the best line, or we can also call it best decision boundary. Here, the decision boundary can be used to separate the two classes very well. Here we can see it has a certain distance to the both classes. Next, let's look at how SVM works. Here we still take linear SVM as an example to explain the theories. Here let's look at this application problem. So in the data examples, we have two classes. Circles denotes -1 and black dots denote +1. Let's suppose we define a function f equals wx plus b. When wx plus b is positive, the output of the function f is 1, and when wx plus b is negative, the output of f is -1. Then we can classify the two classes using this function, right? Similarly, we can define another line like this. It can also classify the two classes. Or the line could be like this. It can still classify the two classes correctly. So from this figure, you can see we can define as many lines as possible to classify the two classes correctly. So here we can see any of them would be fine to classify or to separate the two classes. But here the question is that which line is the best? So here SVM aims to find a large margin between the classes. Here the margin can be defined as the width that the boundary could be increased before hitting a data point. So here, let's say the black line is the classifier, and here this yellow area can be defined as the margin. So the margin represents the width of the boundary. Here you can see if we increase the width of the margin further, then it will hit the 2 points here and here. So the best classifier is the classifier with the maximum margin. So SVM aims to find a large margin between the classes. Now let's look at another concept called support vectors. Support vectors are those data points nearest to the hyperplane. Here we can see the 3 data points. They are close to the hyperplane. We can call them support vectors. This is also where the name of support vector machine comes from. Now let's look at how to calculate the margin width from the previous example. We define a function f equals wx plus b, and when x is positive, wx plus b equals 1. When x is negative, wx plus b equals minus 1. Based on these 2 equations, so if we use the first one minus the second one, then we will get the third equation, like this. From the third equation, we can get the formula in the right side. So there's a relationship between the margin width and the parameter w. Next, let's understand the principle of support vector machine from the mathematical perspective. Let's say there's a set of training examples, dataset D, which can be represented or denoted like this: x1, y1, x2, y2 to xr, yr, where xi is the input vector in a real-valued space, and yi is its class label. Here, let's say this is a binary classification problem. So here the output values yi have 2 values, 1 and minus 1. Here 1 represents positive class and minus 1 denotes negative class. SVM finds a linear function which follows the general form below: fx equals wx plus b. Here w is also a vector, so here w is a weight vector. From the text above, we can see xi is also a vector. So if w times x plus b is not less than 0, then yi equals 1, and when w times xi plus b is smaller than 0, then yi equals minus 1. So in this way, this linear function can separate the 2 classes correctly. Now we already know these 2 equations. They can correctly classify all training data. Now we times yi on both the left and right side for the 2 equations. So for the first one, we multiply yi to the left side and the right side. Then we get the third equation here. And for the second equation, if we multiply yi to the left and right side as well, then we can get the same equation shown in the third formula. We know SVM aims to find a classifier that maximizes the margin. So we can get this equation. If we transform this equation, we can get the equation in the below. So this can be converted to a quadratic optimization problem to solve W and B. So this one is beyond the scope of our lecture. So here we will skip this problem. In the previous slides, we introduced linear SVM. As you know, in the real-world applications, most of the problems are not linearly separable. So for the data sets that are linearly separable, we can use linear SVM to classify them. But how about dealing with the data sets that are non-linearly separable? As shown in this example, we have two classes here, blue points and red points. From this figure, we can see there's no line can separate them correctly. But from this figure, we can see they are still separable. For example, we can use this circle, this dashed line, to separate the two classes. So for nonlinear SVM, the general idea is that the original input space can always be mapped to some higher dimensional feature space where the training set is separable. As shown in the left figure, we have two classes. They are nonlinear separable. However, if we transform this data space using a kernel function, we will get the data points shown in the right figure. Now we can see we can use the decision boundary or hyperplane to separate them correctly. So the solution is to use a kernel function. The core idea is to map the original data sample to the high dimensional space through kernel function. Here's another example. This dataset cannot be separated by a linear function, but can be separated by a quadratic one. Here we can see we can use this curve, this function, to separate the two classes. Here are three commonly used kernel functions, including polynomial function, Gaussian function, and sigmoid function. Next, we will move to another classification method called decision tree. First, let's look at the definition of decision tree. Decision tree aims to create a tree-like model that predicts the value of a target variable by learning simple decision rules from the data features. The figure in the right side shows a simple decision tree. Here we can see each internal node tests an attribute. Each branch represents an attribute value, and each leaf node assigns a classification. This example shows a problem whether it's suitable going outside to play tennis based on weather conditions. So if it's sunny, Then we will consider humidity. So here humidity is the attribute. So here humidity is the internal node, and each branch corresponds to attribute values. Like here the humidity value is high or normal. Each leaf node assigns a classification like yes or no. Will go to play tennis or will not go. And wind is another internal node, and here we can see the attribute values. Wind is strong or weak, and leaf node yes or no. So this is an example of decision tree. Now let's look at the process of decision tree. First, we assume attributes are categorical now. So for the variables that are continuous, we can still convert them into categorical variable. For example, we can set up a threshold, then we can transform a continuous variable into a categorical one. In the second step, tree is constructed in a top-down recursive manner. At the start, all the training examples are at the root, and the data examples are partitioned recursively based on selected attributes. Here, attributes are selected on the basis of an impurity function, such as information gain. We will introduce what is impurity and information gain in our later slides. Here are some conditions for stopping partitioning. The first one is that there are no remaining attributes for further partitioning, or there are no examples left. So it means we have classified all the data examples, then we can stop partitioning. Now let's go back to this example. Should I go to play tennis based on weather conditions? At the root node, which is Outlook, Outlook has some values: sunny, overcast, rain. If it's overcast, then the output is yes. If the value is sunny, we will further test other attributes. Here, humidity is selected. For example, if humidity value is high, then the prediction is no. If humidity value is normal, then the prediction is yes. And in the right branch, if the value is rain, we will further check the wind attribute. If the wind value is strong, then the output is no. When the wind value is weak, then the output is yes. So here we can see a number of decision rules are generated or learned from the data examples. Based on these rules, we can predict the output. Here the output are two values, yes or no. However, here we may find two questions. The first one, which attribute should be selected at first? So you may have a question here, why we select Outlook first rather than humidity or wind? The second question is that, how can we quantify the quality of a split? So how can we know whether this split is good or bad? So in our next content, we will answer these questions. Before I introduce the series, first let's look at another example. In the right figure and the left figure, there are two cases. They selected different attributes to partition the data or to classify the data. According to your understanding, do you think which one is better? Intuitively, the left one is better. Here we can see in the leaf nodes, they are pure. It means we can use patron attributes to split the data examples correctly. And in the right side, we can see for each leaf node, they have two classes, the red one and green one. It means the type attribute cannot split or classify the two classes very well. So here we can see a good attribute splits the data into subsets that are ideally all positive or all negative. So it means that if an attribute can classify the classes very well, then it's a good attribute. Otherwise, it's a bad attribute. Now let's look at one concept, which is called entropy. In the context of training decision tree, entropy can be roughly thought of as how much variance the data has. Here we can see an example here. We can also use entropy to describe impurity of a set of examples. If entropy equals 0, then we can say the dataset is perfectly homogeneous. If entropy equals 1, then we can say the dataset is heterogeneous. In the right figure, we can see all the points belong to the same class. The entropy equals 0, so it has minimum impurity. In the left figure, we can see there are 6 red points and 6 green points. The entropy equals 1, which represents maximum impurity. And we have another example in the middle, so the entropy value is between 0 and 1. So here we can use entropy to describe the impurity of a set of examples. Now let's look at how we can calculate entropy based on a set of data examples. So this is a formula for calculating entropy. Let's imagine we have a dataset D, and this dataset contains C classes. Here PRCJ is the probability of class CJ in the dataset. So given a dataset, we can always calculate the probability of each class. Here the probability of each class equals the proportion of each class in the dataset. Here we use entropy as a measure of impurity of dataset D, or a measure of information in a tree. So these two ways can be used interchangeably. Now let's look at an example how we can calculate entropy given data examples. Let's say the dataset D has 50% positive examples. Here the probability of positive class equals 0.5 and 50% negative examples. Here the probability of negative class equals 0.5. So based on the formula, we can get the entropy of dataset D equals 1. It means it has maximum impurity. Here's another case. Let's say the dataset D has 20% positive examples and 80% negative examples. It means we can get the probability for positive classes equals 0.2 and the probability for negative classes equals 0.8. Based on the formula, we can get the entropy of a dataset D equals 0.722. And in the third case, let's say the dataset D has 100% positive examples and 0 negative examples. Then we can get the probability for positive equals 1 and the probability for negative equals 0. Based on the formula, we can get the entropy of dataset D equals 0. Here we can see as the data become purer and purer, the entropy value becomes smaller and smaller. So in the third case, we only have one type of examples. So we have minimum impurity, and in the first case, we have maximum impurity. Now let's look at another concept called information gain. Information gain refers to the expected reduction in entropy caused by partitioning. So here we can say information gain equals how much entropy was removed by partitioning. So here higher information gain corresponds to more entropy removed. So here information gain actually can be used to measure the quality of the split by weighting the entropy of each branch by how many elements it has. Now let's look at how we can calculate information gain. Given a set of examples dataset D, we first compute its entropy. We have introduced this formula in the previous slide. Next, let's imagine we select attribute AI as the root of the current tree. This attribute AI contains V values. If we partition the data examples based on attribute AI, this will partition dataset into V subsets because it contains V values. Then we will get V subsets D1, D2 till DV. The expected entropy for AI can be calculated based on the second formula. The left side is probability for each subset because we know the number of examples in each subset. We also know the number of examples in the whole dataset. So it means this number can be calculated. And next, we can further calculate the entropy for dataset D1, D2, and DV. Then we can get the entropy of dataset for attribute AI. Based on the two entropy values, then we can get the information gain. We use the entropy of dataset to subtract the entropy of dataset for attribute AI. So the difference is the information gain. So here information gain by selecting attribute AI to branch or to partition the data can be calculated based on this formula. When we build the decision tree, we always choose the attribute with the highest gain to split the current tree. The objective is to reduce impurity or uncertainty in data as much as possible. So we can say a subset of data is pure if all instances belong to the same class. Now let's look at another example and see how we can use decision tree to deal with this classification problem based on all the methods we introduced in the previous slides. So let's imagine a bank received a number of applications to get the loan, and for each application it includes the age of applicant and whether the applicant has a job, whether they own a house, and their credit ratings. And in the right column are the labels. Yes means they can get loan, and for the no means they cannot get loan. Now let's look at how we can use decision tree to classify these data examples. Now let's look at how we can deal with this data shown in the red figure. In this dataset, there are 15 data examples. First, let's look at the entropy for this dataset. From the right column, we can see we have 6 no values and 9 yes values. Here we can calculate the entropy of dataset. Then we get the entropy value equals 0.971. Next, we calculate the entropy of a dataset for each attribute. Here we first take own house as example. From this column, here we can see there are 6 true values and 9 false values. Based on the true and false values, we can split the dataset into 2 subsets, D1 and D2. Based on the 2 subsets, we can calculate the entropy values based on own house attribute. Here we get the entropy value equals 0.551. Next, we calculate the entropy of a dataset based on age attribute. Here we can see for age attribute, there are 3 different values. Here we can see there are 5 young values and 5 middle values and 5 old values. So here, if we split the data based on age attribute, we will get 3 subsets. Each subset contains 5 data examples. So here we calculate the entropy based on the three subsets D1, D2, and D3, then we can get the entropy value equals 0.888. So similarly, we can calculate the entropy of a dataset based on other attributes like has job, credit rating. After we get the entropy values for the four attributes, then we can calculate the information gain. First, we take the age as example. Since we already calculated the entropy value for the whole dataset, which is 0.971, and the entropy value based on age attribute is 0.888, then we calculate the information gain, which is the difference between the two entropy values. The information gain equals 0.083. For own house attribute, we can also calculate the information gain, which is the difference between 0.971 and 0.551. The information gain is 0.42. Similarly, we can get the information gain for has job attribute and credit rating attribute. They are 0.324 and 0.363. Here we can see the own house attribute has the highest information gain. So own house is the best choice for the root. From this whole calculation process, now we understand how should we select or choose the attribute for partitioning. This slide shows the decision tree we built based on these data examples. So first, we choose own house to split or partition the data. We will get 6 examples. These examples correspond to yes values. It means these 6 labels can be classified directly based on own house attribute. There are still remaining 9 labels or classes cannot be classified, and then we use a similar way to choose the next attribute to partition the remaining data examples. Here we select has job attribute. If the value of has job attribute is true, we can get 5 yes labels. If the value of has job attribute is false, we can get 4 no values. After 2 times of data partitioning, we can classify the 15 labels correctly. This is the whole process to deal with this classification problem using a decision tree. Next, I will introduce some disadvantages of decision tree. First is overfitting. A decision tree may overfit the training data. It means the decision tree can achieve good accuracy on training data, but poor performance on test data. Here are some same terms for overfitting. For example, the decision tree is too deep, and there are too many branches. Some of them may reflect anomalies due to noise. In these cases, the decision tree could be overfitting. Here are two approaches to avoid overfitting. The first is called pre-pruning. It means to stop construction early. Actually, for this method, it's difficult to decide because we don't know what may happen subsequently if we keep growing the tree. The second method is called post-pruning. It means to remove branches or subtrees from a fully grown tree. This method is commonly used. And here, a validation dataset may be used for pruning as well. So we can use post-pruning method to avoid overfitting in decision tree. Here are some advantages of decision tree. First, it's simple to understand and to interpret, and the trees can be visualized. Second, it requires little data preparation, so we don't need to do any data normalization or some other data preparation. Third, the cost of using the decision tree is low. The fourth one is that it's able to handle multi-output problems. The last one, it uses a white box model. It means the explanation for the condition is easily explained by Boolean logic. So here are some advantages of decision tree. And here are some disadvantages of decision tree. First, decision tree learners can create over-complex trees that do not generalize the data well. It means overfitting. Second, decision tree can be unstable because of small variations in the data. The last one, decision tree learners create biased trees if some classes dominate. Therefore, it's recommended to balance the dataset prior to fitting with the decision tree. So we have introduced data balancing methods in our regression lecture. In the last part, I will show you some applications of classification in GIS. The first application is about landslide susceptibility mapping. Landslide susceptibility mapping is very important for improving disaster management and designing mitigation strategies. Here are some steps about landslide susceptibility mapping. First step is to determine the classification problem, because the output is to determine the high susceptible area and low susceptible area. So the output is categorical. We can take it as a classification problem. The second step is to prepare data for training the model. In this study, here are the features selected to train the model for landslide susceptibility mapping. Here we split the features and labels into training data and test data. Here we can see the labels include landslide and non-landslide. And here are some models that are used for classification. The step 3 is to do classification results evaluation. As we mentioned in previous slides, it's important and necessary to calculate multiple evaluation metrics. Based on the different evaluation metrics, we can evaluate the performance of these models. After the prediction, we can further create landslide susceptibility maps. Here we classify the landslide susceptibility into 5 categories. Red color stands for very high susceptible areas, and green color represents very low susceptible areas. The left figure shows the results for logistic regression, and the right map shows the results for support vector machine. The second application is to predict travel activity purpose. As you know, with the rapid development of GIS and GPS technologies, we can collect a lot of trajectory data of vehicles and people and analyze this trajectory data using GIS methods to create useful information and knowledge about travel activity patterns. This is very important for urban planning and transportation management. So this application is about travel activity purpose prediction or imputation using GPS trajectory data. These two figures show the trajectory data. The left one shows the taxi trajectory data, and the right figure shows the GPS trajectory data. First, let's formulate the problem. In this case, it aims to detect cab drivers' dining activities in the city based on taxi trajectory data. So we can take it as a classification problem because we will check or predict activity is dining activity or not. Here's the solution. First, we find cab drivers' stay activities from trajectory data and identify the dining activities. It means these stay activities will be classified as dining activities and non-dining activities. Here, one question is that how to distinguish dining activities with other stay activities, such as refilling behavior, waiting for passengers, and some other stay activities. So here we can see this is a classification problem, right? Now let's look at how it works. In step 1, stay activity will be detected from the taxi trajectory data. The left figure shows a sketch map of state activity detection. When taxi is moving, we can see taxi trajectory points has a certain distance between each other, and when taxi is parked or stay in an area, we can see the trajectory data points will be clustered in an area. So in this way, we can detect state activities from taxi trajectory data. And from the figure B, we can find the state activity in real taxi trajectory data. We can see in this road intersection, there are a lot of trajectory data points clustered here. So this could represent a state activity of taxi drivers. Step 2 is to extract features to classify cab drivers' state activities. Here, 4 features were chosen for this prediction. The first feature is distance to the nearest restaurant. It's defined as the minimum distance between the stay point and the surrounding restaurants. The second feature is about the probability for dining. It also depends on other points of interest around it. The third feature is about distance to the nearest road segment. This is because a cab driver usually parks his or her taxi on the road next to the restaurant while dining. And the last feature is about activity duration. This is because duration of a cab driver's dining activity is usually between 3 and 16 minutes. Based on the 4 features, in step 3, a training classifier will be trained to identify dining activities. Here, SVM is selected to identify dining activities. This is because SVM has high accuracy and nice theoretical guarantees regarding overfitting, and is also very suitable for binary classification problem. In step 4, the model performance will be evaluated based on the evaluation matrix. Here the model was evaluated using 5-fold cross-validation on the training data. Here we can see the average evaluation matrix for accuracy, precision, recall, and F1 score. After the classification, we can further do more spatial and temporal analysis. For example, we can map cab drivers' dining activities in the study area across time and space. Here we can see the spatial variations of cab drivers' dining activities from Monday to Sunday. Of course, there are some other applications of classification in GIS, such as land use land cover classification, remote sensing image classification, susceptibility mapping, transport mode recognition, etc. Here are some references and also the 2 papers we selected for the applications. So if you want to know more details about these applications, so please feel free to read these papers.